To start the session, we call Professor Alain Aspect, Institute d'Optique.
Do we go? Okay. If Vanderlei was here, I would thank him. Vanderlei? No, it's not. Vanderlei is requested here. Vanderlei? Okay. Vanderlei, I want to thank you for the privilege to be here. Is it too strong? For the privilege to be here, although I am not a former student of Dan Kleppner. I saw Dan for the first time at ICAP in '78. It was in MIT. But I was a small guy watching the big hero presenting surprising ideas, surprising for me, about Bose-Einstein condensation of atomic gas. And I must say that I missed a lot in your talk, and not only because of my ignorance of English, it was also because of my ignorance of that kind of physics. And I am pretty sure we did not interact at that time. I think the first interaction happened 4 years later in Gothenburg, in another ICAP. I was still an undergraduate, but I have been invited to give a plenary talk about the results of the Bell's inequalities. And I was a little nervous, especially about quotients. My charming chairman, Norman Ramsey, had told me that he would keep control, and if the quotient became bad, he would keep seriously control. And the first quotient, a gentleman stood up. It was our first interaction. And the question was, young man, can we consider that the question is settled now? And you know, I never thought out if it was friendly or ironical. But it was you, yes, you. This was a question. But the way I understood the question was, okay, young man, now you have played with this foundation of quantum mechanics. It's time to go to serious stuff. I followed the advice a couple of years later when Claude Cohen-Tanouji asked me to join him and John Dalibard to start research on laser cooling of atoms. And this offered the opportunity to meet you and me more and more often. I often benefited of your hospitality in Belmont. And believe it or not, I was even offered the privilege to rattle the leaves on his lawn in autumn. And I can tell you, American leaves are much bigger and abundant than European leaves. But it was a sign of friendship. I had then the wonderful privilege to discover B and Dan, this wonderful person, so cultivated, with whom we could speak of politics, art, literature, family. And when B was not around, we could even speak about physics. And I know she is not Beatrice screaming, okay? She's not. And although I was not your student then, I've benefited a lot of this discussion about physics, but I want to say that I am pretty sure that among all your achievements, the one which has played a major role in my evolution, my understanding of physics, is, again, it has been cited so many times, but it's a fact, it's the work on the inhibited spontaneous emission, with the founding paper that you signed, and then with the wonderful experiment that was done by Randy. This really changed my vision and or my understanding of quantum mechanics. And for this reason, today, or at least it's one of the reasons why today, I want to speak about Anderson localization, because I think that there is a similarity. Suppressing spontaneous emission, suppressing the motion of atoms, and this for a very fundamental quantum question, I think there are similarities. So if you allow, I will start and speak about Anderson localization. Here we are. And yes, this is a phase. I missed the word that Rick was using. But I like very much this photo because it's both friendly, but you also expect a question which might be not so easy to answer. Okay. Fortunately, there is B behind who is keeping things under control. So let us start. So this is Anderson, and this is Mott, the two heroes of Anderson localization. This is my group, a little bit of advertising for the young people who are around. Don't hesitate to join us. And I must do it now, otherwise I will forget. I have wonderful collaborators. We started the work on Anderson localization with Philippe Bouillet, who now moved to Institut d'Optique in Bordeaux. We have a branch in Bordeaux. The wine is better in Bordeaux than in Palaiseau, for sure. And I have two young team leaders, Vincent Josse and Thomas Bourdel, plus the theory team leader, Laurent Sanchez-Palencia. Okay, let us start with the naive idea of an AMO experimentalist about Anderson localization. At the beginning, it took me some time to understand why people were so excited, but I found the reason in reading all paper by Mott. The problem is the following. If we consider the Drude model of conduction, electrons are bouncing on impurities. And when you increase the amount of impurity, you easily understand that conductivity decreases. But this model cannot tell you that conductivity is totally cancelled at some point. And the model which was proposed by Anderson is a model based on quantum mechanics where precisely beyond a certain level of disorder, then it's not only reduced conductivity, it's a totally cancelled conductivity. This is a problem that people wanted to solve. The model of Anderson is a model of condensed matter physics. We heard of that this morning by Massimo. It's a model in which you have the tight binding model where electrons jump by tunneling from one side to another side. And when the matrix elements for tunneling are large enough, then you have an extending wave function. And what Anderson did is showing that if you add disorder by pulling the bottom of the wells up or down, and the amount of disorder is proportional to the spread here in the bottom of the energy, then he showed that at some point, rather than an extending wave function, you have a wave function with an exponentially decaying profile. For people working with waves, like us, the idea is slightly different, but there is an equivalence between the two models. The idea is the following. In a perfect medium, we have a wave propagating freely. This is equivalent of that. But if we add scattering centers, when the rate of scattering is large enough, rather than propagating like that, there is a moment where the wave can no longer propagate. I again make a little advertising with this paper that we wrote with Massimo and where we explain all that. Doesn't want to work? Okay, let's do it this way. Now I want to flash rapidly a naive and a simple way of understanding Anderson localization, which is useful because it allows to emphasize the most important ideas. The idea is the following. We have a wave traveling, trying to propagate here, and let us start by a scattering here. Then I can have multiple scattering, and after a series of scattering, I come back to the origin. And I have many loops like that coming back to the origin. If all these loops come back to the origin in phase, there is a constructive interference to come back to the origin. And if there is constructive interference to come back to the origin, of course, there is a big suppression of the propagation. This image is very interesting because you can draw many things from that. First, you understand that the simplest way to have everybody coming back in phase to the origin is to have a phase which is less than 1 radian. So if the mean free path is much less than the wavelength, it's clear that the size of the loop here is much less than 1 wavelength, and so everybody comes back in phase. And this is a famous Joffé-Regel criterion for saying that the mean free path has to be definitely smaller than lambda, or lambda divided by 2 pi. And this image allows me to emphasize important features of Anderson localization. First, Anderson localization is about interference of many scattered wavelengths. Second, It's a single particle quantum effect. What I am describing here is a wave function describing a single electron, a single atom, a single photon. It's a single particle effect. Finally, this image allows to emphasize maybe the most important character, which is the role of dimensionality. Because everybody knows that returning to the origin by a random motion is very easy in one day. If you propagate on one day by a random motion, you are soon to come back to the origin. You are sure to come back to the origin very soon. In 2D, a random motion brings you back to the origin only after a quite long time. And in 3D, don't even dream about it. You will never come back to the origin, okay? And so you understand the strong role of dimensionality. It's very easy to localize in one day. It's very difficult in 3D. This is why you have this criterion, the Joffe-Regel criterion, which is very demanding here. And in 2D, that's a marginal case between the two situations. So I like very much this image because it allows to understand this fundamental feature, which can be demonstrated by very sophisticated theoretical reasoning. Doesn't work. Okay, I will skip that rapidly, otherwise Vanderlei will be very unhappy. But people have tried for decades to observe Anderson localization with waves. And let's suppose you try to do it with light. What will be the main problem? You want to have a very short mean-free path. Because you want a very short mean-free path, you want to have particles scattering strongly, which means a large contrast in the index of refraction. But when you have a large contrast in the index of refraction, it's very difficult to avoid some absorption. So let's suppose that you observe that there is an exponential decay. I am going to claim Anderson localization. People are just going to tell me, no, there is a residual absorption, and what you observe is just the usual Baire-Lambert law. Okay? And so the difficulty for people trying to observe Anderson localization with light is to demonstrate that the exponential decay that they observe is not due to absorption. Eventually, finally, there are a series of experiments which are convincing, notably in Florence, also in Constance. And there are experiments in 2D and 1D. One is in the Weizmann Institute, the other one in Technion, which work. There are also a series of interesting experiments with acoustic waves, but I have no time to describe them. Now, of course, if I emphasize the difficulty for other people, is to publicize, to advertise cold atoms, okay? And in particular, cold atom in laser speckle. Why is it so nice? For many reasons. All of you know that now with the experimental techniques that we have, we can control the dimensionality. We can work 1D, 2D, 3D. We can have wavelengths easily between controllable over many order of magnitude. It's just a matter of which temperature we have. We have pure potential, no absorption, provided that we are far enough from the resonances. And last and not least, compare, for instance, to people working in condensed matter, we have many, many observation tools. You know that. I don't go into details. Of course, with cold atoms, there is a new feature, which is the fact that there are interactions between atoms. And I insisted that Anderson localization originally is about single particle. But as Massimo showed this morning, the reason why Anderson attacked the problem of single particle localization is because it could not work on the problem of interacting particle. So we first attack non-interacting particle, but when they interact, the problem becomes even more interesting. And of course, it is a problem which interests very much theorists. Now, cold atom is very nice. We all know that. When we embarked in that, speckle was not very popular. The reason why speckle is very nice, according to what we have found, is that speckle actually is a disorder which is extremely well known. To make a long story short, we pass a laser beam through a scattering plate, which is a plate with a random phase on the plate. And that means that the classical electric field that I get anywhere here is the sum of many random variables. And so I can apply the central limit theorem, and I know, and this has been verified for decades by people doing optics, that I have a Gaussian random process. Be careful. What is Gaussian is the electric field. And our potential is proportional to the square modulus of the electric field. But we know that the Gaussian process has a wonderful property that all higher order moments can be expressed as a second order moment. And for this reason, the speckle is a very nice disorder that we master and that we understand. In particular, there is a nice property which is useful in our experiment. It is the fact that the distribution of intensity in the speckle is maximum for an intensity which is 0. In other words, in a speckle, there are many dark places, and this will be important at one point. Okay, now, one-day Anderson localization. I will be fast here, because I don't want to make Vanderlei unhappy. And I have something more interesting to say. So one-day Anderson localization, theorists tell you there is no interest in studying Anderson localization because we have a general theorem that everything is localized. Whatever you do, you always have localization in 1 day. Well, for us experimentalists, the situation is a little more subtle. Because, for instance, if I am in a situation where the localization length is 1 kilometer, and the size of my experiment is 1 millimeter, it's just like being non-localized. Okay, so let us investigate a little more. And when you think a little more, look a particle moving in a speckle potential here. If the energy of the particle is less than the height of two large peaks, particle bounces between the peaks. It's localized. The theorem is true. It's not very exciting, right? But then if you solve Schrödinger equation numerically for a situation where now the energy of the particle is much larger, like 10 times larger than the height of the peaks that you have here, anyway, when you solve the Schrödinger equation, you find a solution with exponentially decaying amplitude. And this looks like Anderson localization, because this can be understood only by the fact that you have many scattering on the small peak, and the coherent addition of all these waves prevents the main wave from traveling. Okay? So when we saw that, we decided to observe it, and so the experiment is no mystery for people who are here. We have atoms traveling in a focused laser beam, which is exactly horizontal, so they travel freely one dimension. We shine a laser speckle, which is produced by a narrow slit, so that the speckle pattern is just like discs like that, which are much broader than the size of the tube of the guiding laser. So that for all practical purposes, because our atoms are cold enough, we are really one dimension. The atoms circulate like that. They are in the ground state of the transverse harmonic oscillator, and the speckle pattern is broad in this direction, but it's very sharp along the z direction. Okay. So with this, what do? We load a BEC here. There is some interaction energy, and then we remove the longitudinal trapping so that the BEC expands. The beauty of it is that we know that there is a maximum velocity which is associated with the initial chemical potential, so we know that there is a maximum velocity, and then we observe what happens. So if there is no speckle, no disorder, then we see a ballistic expansion. Here, the interaction energy is transferred into kinetic energy, and then there is no more interaction energy, and we have just a ballistic spread of the wave packet. Now, what do? We add the disorder, and then after some time, we take a photo. We all know that we can take a photo by just shining resonant laser and doing an absorption image. And this is a real image. It's not an artist view. This is a real image of the profile of the expanding BEC in a regime where we apply the disorder, which means that it starts expanding, and then after a fraction of a second, 1 second, 2 seconds, after a fraction of a second, it stops expanding. And then you can look at the profile which is here. And we are exactly in the situation where the kinetic energy of the atoms, I remind you that we know the kinetic energy because it corresponds to the initial chemical potential. This kinetic energy is 10 times larger than the typical energy of the speckle. So we are really in the regime where the atoms fly high above the mountains, but anyway, we have this exponential profile. To my knowledge, it's the first time that people could see an exponentially localized, Anderson localized wave function. Okay, so here I will skip the fact that, yes, indeed, it's exponential profile. We can fit with the theory. Everything works beautifully. I have just to mention that other groups have been working on that. Massimo told about what they were doing in Florence. It's a different approach of disorder. Rather than having speckle, they have this bichromatic potential. Randy Hewlett has been doing a beautiful experiments. There is also a series of experiments which are related, which is called dynamical localization, which is localization in p-space, in momentum space. Mark Reisen was a pioneer of that, and there is a group in France, in Lille, who is doing a beautiful experiment on that. It's related, but somewhat different. This was to warm up. The serious stuff is Anderson localization in 3D, as I told you, because in 3D it becomes really difficult, but after a lot of effort, we succeeded. First problem in 3D, in 1D, you can hold the atoms in the laser beam. In 3D, gravity is annoying. So what do? We switch off gravity. So to switch off gravity, we take advantage of the fact that we work with rubidium atoms. They are paramagnetic. We select a Zeeman sublevel, and we apply a gradient of magnetic field. And then we compensate gravity. As you know, the problem is that nothing is perfect. And if you have a gradient like that, because of Maxwell equation, divergence B equals 0, there is a radial component. So to take into account this radial component, we do two things. First, the coils are calculated big enough that this radial component is not too annoying. And second, we choose a configuration where the radial component would expel the atom. So if we observe localization, you cannot tell us that it is because there is something attracting towards the center. If you would choose the opposite situation, there could be argument. Second difficult thing when you are 3D, so now we have atoms, and they are here, the Bose-Einstein condensate is here, and when we release everything except this vertical gradient, we can keep the atom and observe them for several seconds, okay? And we observe them by some absorption imaging, standard technique. We have a resonant laser, and we make an image here, and we measure the column density. Now, the second problem is how do we do a three-dimensional speckle? Of course, theorists would tell us, okay, make a 4 pi light coming. We all know that this is totally impractical. But when you think a little bit of it, it seems that if you have a laser passing through a scattering plate here and making a speckle along this direction, and the same laser, or the laser coherent with the first one, coming along that direction, then you can repeat my argument. What you receive here, as an electromagnetic field, is a sum of many random variables, and now I have a speckle in 3D. Of course, it's not exactly isotropic, but it's really a speckle along with a short correlation range along any direction in space. Of course, for the argument to be correct, we must be sure that everything interferes here, but it is a case if we choose a polarization perpendicular to the plane which is here, that is, we choose a polarization along y. And with this, it's a real speckle. That is to say, the distribution of intensity is still an exponential one. It's not isotropic, but the autocorrelation radius along each direction in space is very small. In that case, whatever the direction is always less than 0.3 micrometer. We have large aperture objectives which are here. So we have a speckle which looks like that in 3D. And then we do the experiment. How do we do the experiment? We have the trapped Bose-Einstein condensate here, which is in an optical trap. We condense in an optical trap. And then at time t equals 0, we let it expand. It does not fall because we suspend, because we compensate gravity. And then we switch on the disorder as soon as the interaction energy is released and transformed into kinetic energy. And then we observe what happens. For a small disorder, we see that after 1.2 seconds, we can no longer see anything. Then there is no more signal. It expands, and there is not enough absorption that we can detect it. But if now the disorder is larger, the amplitude of the disorder is larger, we see that it begins to expand, and then there is something which survives. Here we have 6 seconds, but it continues until we can observe it until 8 seconds, 10 seconds. The images are not as nice, this is why I don't show them. Okay? So how do we analyze that? We use a phenomenological model which does not use any specific theory, apart the fact that we assume that we have a fraction which is localized plus a fraction which makes a standard Brownian motion. If you have a standard Brownian motion in 3D, you expect that the density at the center will decay as 1 over t to the 3/2. But because we integrate along one direction, it's a column density, we expect that it will decay as 1 over t. So we fit here on the density at the center, we fit 1 over t plus something. In the case of weak disorder, the asymptote is 0, there is no localized fraction. But in the case where we have the large disorder, then this asymptote of the 1 over t decay goes to a value here, and we take that as a measured localized fraction. And there is always a diffusing fraction where you can see that the squared RMS size increases linearly with time, and we can measure the diffusion coefficient for the non-localized fraction. So with this, we think we really demonstrate that we are in a situation where we have a localized fraction and a non-localized fraction. Now, can we be in a situation where all the atoms will be below the so-called mobility edge? That is to say, all atoms are localized. Unfortunately, with our system, no, but we hope sometime we are going to have it. And the reason is the following, and the reason was found when trying to make a theoretical analysis. The problem is the following. As I told you, we let the cloud expand, and then we ramp up the disorder. When the cloud expands, the spread in energy of the atoms is very small. But when I ramp up a disorder, now I have a big spread in energy in the atom, which corresponds to the spread in the potential energy due to this disorder. And so it turns out, when you look at the numbers, that we are always in a situation when a fraction of the atom will have an energy too large to be localized, and a fraction of the atom which have an energy which is low enough to be localized. So there are plenty of calculation. We have compared the result of this calculation, which are quite difficult, but we have a good theory group, with the observation. They need one adjustable parameter, which is good news. It means that not everything is understood. There is something to understand. And let's say that we have demonstrated 3D Anderson localization, and that we have not been able to measure the exact value of this threshold for localization because the spread in energy is too large. And, well, we could announce a number, but we think that it would not be nice. I must say that an experiment has been done, an experiment in the same spirit, but in really completely different configuration, has been done by DiMarco in, where is he? Urbana-Champaign? DiMarco? Well, yes, Urbana-Champaign. Okay, so what is the situation for localization in 3D? We have directly observed the fact, I think there is no doubt, that there is one diffusing component and one localized component. We have made a phenomenological, I mean, it relies on basically no theory except that we understand Brownian motion. We have a phenomenological measurement, which is not theory dependent, of the localized fraction and of the diffusion coefficients. And localization cannot be explained by any classical reasoning. What could be a classical explanation for localization? Percolation. You know what is percolation. We have mountains, there are passes, and if you are below the pass, you are stuck in a valley. I emphasize that with a speckle, the probability to have 0 is very large, which means that actually when we calculate the percolation threshold, it's less than 1% than the average altitude of the mountains, which means that what we observe cannot be explained by a classical trapping below the percolation threshold. Another hypothesis could be that we have local minima and that we are trapped in these local minima. It turns out that if you calculate the possibility to trap atoms in these local minima, we are always in a situation where the first level of the harmonic oscillator would be over the altitude, the edge of the trapping potential. So it cannot be in each individual minimum that we are trapped. So the only conclusion is that it has to be a collective trapping, and a collective trapping is exactly what is Anderson localization. So it's hard to conclude that it is not Anderson localization, but we think that something is still missing in our experiment. What is missing is the smoking gun that coherence plays an important role. Because Anderson is really something extremely coherent. So we would like to have a proof that coherence plays a role. At this point, we have decided to study a localization phenomenon, which is simpler than Anderson localization. It's called weak localization. And to demonstrate that, yes, we are on the way of having a real coherent phenomenon. So what we have done is studying coherent backscattering. This is how we have done the experiment. We have observed coherent backscattering in 2 dimensions, and this is the way we do the experiment. Now here, we have only one of our plates for making the speckle, but now this plate is not a thin slit, it's really a big aperture. So you have to think of the speckle as grains like that and with some Rayleigh length. So it's just like many rods randomly placed, okay? So we have rods like that along the x direction, and we are going to launch the atoms in the zy plane. So we are going to observe 2D evolution of the atom because we launch them in the symmetry axis of this problem. Now here, what are we going to do? We are going to launch the atom, and at a certain moment, we switch off everything, we switch off the disorder, and we let the atom expand. But again, we have still this compensation of gravity, so we can make an extremely long time of flight, which allows us to have a very good accuracy in the measurement of the velocity. So first, we do that at time t equals 0, and here is a plot of the velocity in the 2-dimensional plane that we have here. So it's a plot of py, pz. Why not px? Because again, we make a column density along this axis. So we measure the velocity in the plane. And here, for those who can look at this picture, you have the beautiful demonstration that at time equals 0, we have atoms with an extremely well-defined velocity along a precise direction. Here is a number. The velocity is 3.3 meters with a spread of 3.3 millimeter per second with a spread of 0.2 millimeter per second. It's a real tour de force. The way they do it is the following. It's a so-called delta kick cooling method. The atoms are confined here, and at time t equals 0, you let them expand. And suddenly, for a short amount of time, you apply again an harmonic potential in 3D for just the right time to stop all the atoms. Because if you let the atom expand enough, the atoms which are farther are faster, and you will apply an harmonic potential which will exert a stronger force. And so it's miraculous. You let the atom expand, you apply the harmonic potential, and then everybody is stopped. Really stopped. And then you apply a gradient timeout already. And then I'm finished. And then you apply a delta kick, a kick, a magnetic kick, and then all the atoms go like that. And then I show you the picture. So initially, all the atoms move along this axis, and after a while, you see the atom, the momentum of the atom, on a circle. Why? It's elastic scattering. Elastic scattering means the modulus of the momentum is conserved. So they scatter on a circle, but then after a while, what you see? You have no longer any remembrance of the initial direction, but there is a peak in the backward direction. This is a coherent backscattering peak. I'm not going to explain in detail because I promise not to be too long. But the fact is that we can explain easily this peak with very simple concepts. It doesn't demand big theory. And this is really a smoking gun that in the phenomenon we have coherence. So this is called weak localization. It's the first appearance of a localization phenomenon. If you go with a bigger effect, then you are going to have diagram, you are going to have coherent backscattering here, coherent backscattering or backscattering, a series of diagrams, and when you make a resummation of all these diagrams, you get Anderson localization. So this is what we want to explore. So with this, I can just tell you what we are going to do. We are going to achieve a better control of the atom energy in disorder. Rather than having a beam spread, we are going to have a narrow spread in the energy of the atoms. And with this, we are going to study more and more. We will add control interaction, which is a big challenge for theory. And with this, I think we have a quantum simulator. I just want to finish with this beautiful picture provided by Bill. Thank you, Bill.